So this is one example of next concept, that is bonded wire type strain gauge. Bonded resistive wire strain gauges. So see here what happened here. So they have placed some conducting wires on a material. So whenever these wires are stretching in any direction, automatically it will represent some resistance value. So see here, this is the material is bending in 4 directions. Okay, when there is no stress, when there is a tension, then what happened here? You can see clearly here, and you can say, you can measure the resistance variations when the this type of material, this type of resistive type of strain gauge, okay, is varying. So this is an example of bonded type wire strain gauge. Here we have to define the gauge factor of this material. Okay, not all the type of strain gauges are seems to be like this. Some they will form as with straight lines also. So see here, this is an example of our wide strain gauges. So here I have placed these wires in this way. So these are the electrical leads. From this electrical leads, this is the wire we have fabricated on a material. So this is called fine wire, and the background one, this box is nothing but as a supporting bias, and these are the electrical leads, and this is the direction of strain. So we can apply the strain in this direction or in this direction. On both directions you can apply the strains. So anyway you can apply the strain into here. But here in this case the wires are seem to be like as in a vertical direction. So for that reason you have to apply the strain also in the vertical. Like stretching, like we have to stretch in upward and downward directions. Okay. Okay, right. A fine wire element of 25 mm or less diameter is looped back and forth on a carrier or mounting plate, which is usually cemented the member undergoing stress. Here we are going to be whatever the stress we are applying, that material we are placing on a cement base or in a fabric base or a special type of material. On a special type of material we are forming this resistive type wire gauge. With generally this type of wire is consisting of 25 mm or less than 25 mm diameter. The grid of the fine wire is cemented on a carrier, which may be a thin sheet of the paper or bakelite or tefflon. On a paper sheet or a bakelite or tefflon. Based on these materials we are forming, we are taking as in a base for this resistive type wire strain gauge. Bonded type wire strain gauge. The wire is covered on the top with a thin material, so it is not damaged mechanically. So whatever the resistive wire you are placing on one base, we are covered that area also, so we cannot see clearly that resistive type fine wire. The resistive type fine wire will be cemented on this material. Okay, right. The spreading of this wire permits uniform distribution of the stress. When you are stretching this type of strain gauges, the force or the strain will be equally distributed on the total material. The carrier is then bonded and cemented in a member using sturdier. So here the carrier is then bonded. We have a bonded area, regions are cemented on the member being studied. This permits a good transfer of strain from carrier to wire. So whatever the formations or arrangements you are doing, these arrangements are uniformly distributing the strain onto this material. Right. So a tensile stress tends to elongate the wire and thereby increasing its length and decrease its cross-sectional area. The combined effect R is equal to rho L by A, rho into L by A. So here the rho we are representing with small r, where the small r is nothing but the specific resistance of the materials in ohms per meter, where L is the length of the conductor in meters, A area, the area of the conductor factor in meter square, okay, in terms of m square, meter square. So this is about the resistivity length area relationship for the bounded or unbounded strain gauges. So in the bounded strain gauges, we are learning this formula. Okay, as a result of strain, two physical parameters are particularly interested. So whatever it may be, finally we have to focus on two parameters in this strain gauges. The first one, the change in the gauge resistance. What is the resistance value is changing from what is the range of the resistance and what is the effect of this gauge resistance. The change in the length. What is the length behavior? How much length is changing from which value to which value it is changing. These are the things we have to identify. So coming to here, based on these parameters, now we are defining the gauge factor definition. The measurement of the sensitivity of a material to strain is called gauge factor. So the gauge factor we are defining here. The measurement of the sensitivity of a material to strain is called gauge factor. So here, whatever the resistance we are measuring, that material, whatever the material here we are using, that material sensitivity to applied force or strain or maybe pressure, whatever it may be, for applying the strain, what is the sensitivity of the material is nothing but as gauge factor. It is the ratio of the change in the resistance to the change in the length. Here we can give the relationship between this gauge factor with the resistance and length. That is delta R by delta L by L. The gauge factor we are representing with K. Gauge factor with K is equal to delta R by R, delta L by L, delta R by R by delta L by L. So where K is the gauge factor, delta R the change in the internal resistance in ohms or the initial resistance of the ohm in ohms, delta L the change in the length in meter, L the initial length in the meter. So R and L's are initial resistances and initial lengths. Delta R and delta L are the change in the resistance and change in the lengths, and K is the gauge factor. Okay, so this is about the gauge factor definition, and this is the base formula for the gauge factor. Okay, for the strain gauges. For the strain gauges, gauge factor, this is the representation. Let us see the gauge factor derivation. The K value here we are identifying in general case situations. Since strain is defined as the change in the length is divided into original length. So first of all, here we are defining the strain in the parameter of sigma, where here we are taking sigma is equal to del L by L. So whatever the changes in the length, that is del L by L, we are representing as sigma, and we are writing this expression with K is equal to, that is gauge factor. Just now we have written gauge factor K is equal to del R by del L by L. In the place of del L by L, I am representing this sigma. Okay, where sigma is the strain of the lateral direction. The resistance of the conductor of uniform cross-sectional is R is equal to rho L. R is equal to rho L by A, and R is equal to, here the length we are representing with L and area we are representing with pi R square. R is equal to rho R is equal to rho L by pi R square, rho L by pi R square, and R is equal to D by 2. So radius is equal to diameter by 2. So R is equal to D by 2, R square is equal to D square by 4. R square is equal to D square by 4. And R is equal to rho L by pi D square by 4. In the place of R square, I am representing with the diameter. So finally I am writing R is equal to rho L by pi by 4 into D square, pi by 4 D square. So where rho is equal to specific resistance of the conductor, L is equal to length of the conductor, D is equal to diameter of the conductor. Just we are defining the terminology here. Now when the conductor is stressed, when you are applying the stress due to the strain, the length of the conductor is increasing by delta L. So the length of the conductor is changing. The change of that length we are representing with the delta L, and simultaneously decreasing by delta D in the diameter. Automatically the diameter, the area is going to be reduced. Okay, this is why? Because the length and diameter is inversely proportional. When length is increasing with the delta L, automatically with the diameter delta D is reducing. Hence, the resistance of the conductor we are now writing. So the same formula here I am writing. Rho here R is equal to rho L by pi by 4 D square. In the place of L I am representing with del L with L plus del L. In the place of D I am representing D minus delta D. L plus delta L, change increasing in the length, that is I am representing with L plus delta L, decreasing in the diameter, D minus del D, I am representing here. The same formula I have taken from the previous slide. Okay, so in the previous slide we have the formula of this one. So this is the formula here we are taking, rho L by pi by 4 D square. This is the formula here we are taking. In that formula we are substituting L plus, in the place of L plus delta L, in the place of D minus del D. Why? Because it is reducing. So here it is seems to be like as A minus B whole square. So simplify this one. So it will come D square minus 2D into delta D plus del D square. Since del D is small, del D square can be neglected. Generally, del D if it is 0.1, del D square is equal to, it's very less. So automatically we can neglect del D square. So if you remove that del D square, R is equal to rho of L plus del L by pi by 4 into D square minus 2D into del D. So here you can here the pi by we can take the D square from this expression, and after taking D square you will get in the denominator like this, pi by 4 D square into 1 minus 2 del D by D. So this is we are simplifying, and this is the final formula we are getting for RS. This is the RS representation. This is the RS representation. Rho L into 1 plus del L by L. Here I am representing, here I am taking common in the numerator L. In the numerator I have taken L is common. In the denominator I have taken the common is D. I is the D. Finally I will get here del L by L and del D by D. So these are the variations I got in this expression. Now here the del D by del L by L we are representing with mu. Okay, so where del D by D is equal to mu into del L by L. Okay, so by using the Poisson's ratio, we can define the parameters, the axial direction parameters. Mu is equal to del D by del L by L. So this is the expression we are taking from the Poisson's ratio. Okay, right. With this, I am defining del D by D is equal to mu into del L by L. Now I am substituting this expression in the previous expression, that is in this 13.4 expression. In the 13.4 expression, I am substituting this del D by D value. Now, in this entire equation, I have eliminated del D by D, and that expression I am writing with mu into del L by L, where the delta D by D is available. So, after substituting here, this is the expression I got. Okay, so for simplifying this one, I have taken I am multiplying the denominator and numerator with 1 plus 2 mu into del L by L. So I am multiplying this value for the denominator and numerator also. So from this entire expression, I am taking common rho L by pi by 4 d square, rho L by pi by 4 d square. After taking, I got this expression. In this, with this expression, I am simply representing, this is seems to be like as a minus b, this is seems to be like as a plus b. That is a square minus b square. So the above expression I have multiplied, and I am representing the expression in this way. Okay, so finally I got the simplified version for that expression is like this. I got the simplified expression like this. Okay, after you are getting, so this is in terms of brackets. Now this rho L by pi by 4 d square, I am multiplying this value with the internal function of this is the function. So this is 1, this is 1 plus 2 mu into del L by L. So rho L by pi by 4 d square into 1, rho L by pi by 4 d square into del L by L into 1 plus 2 mu. Okay, so this is the expression. So from this expression, I am previously I have the expression R is equal to rho L by pi by 4 d square. So this is the expression here I have. Previously we can see. This is the 13.3 expression. R is equal to rho L by pi by 4 d square. That is I am taking here. Okay, so R is equal to rho L by pi by 4 d square. That is the expression we have taken in the previous slide. This expression, this Rs is equal to, we are representing R plus delta R. R plus delta R. Now here the del R I am writing rho L by pi by 4 d square into del L by L into 1 by 2 mu. So this is the expression I got. How I have represented this expression? So in the place of R, I am substituting this Rs value. I am substituting here, and after substituting this value, I have finally got the del R value like this. In this expression, the gaze factor I am writing like this: del R by R. So here I have del R. Here I have del R. Here I have del R. R value here I have, and del R value also here I have, and now I am substituting del R by del L by L. So this del L by L, this del by L are going to be cancelled. Finally, I am representing the gaze factor value K is equal to 1 plus 2 mu. 1 plus 2 mu. What is the mu? Mu is equal to, here we have defined the new Poisson ratio. That is now Poisson ratio is mu. So the Poisson ratio, where the gaze factor is equal to 1 plus 2 into Poisson ratio. 2 into Poisson ratio based on the axial direction. So this is a bounded strain gaze factor derivation. Okay, right. Now, generally, strain gauge semiconductors have higher sensitivity. Semiconductor strain gauges has very high amount of sensitivity. Okay, so based on this, here we have a problem. The resistance strain gauge with a gaze factor of 2 is cemented to a stream member. That means they given K is equal to 2, which is subjected to strain of 1 into 10 power minus 6. If the original resistance value of the gauge is 130 ohms, calculate the change in the resistance. They have given K is equal to 2, and they have given the change in the which is the subject to strain of 1 into 10,000. That is del L by L. They have given is 1 into 10 power minus 6, and they have given R is equal to 130 ohms. So these are the values they given. Now we have to simplify this, and we have to get the del R, change in resistance we have to find. So from this equation, write down del R is equal to K into R into del L by L. K value 2, R value 130, del L by L 1 into 10 power minus 6, that is equal to 260 micro ohms. So the change in the resistance, the original resistance is 130 ohms. The change in the resistance is 260 micro ohms. So this is the problem. Okay, with this we have completed the wide type strain gauges. Totally we have 3 different types of strain gauges: wide strain gauges, foil type strain gauges, and the last one semiconductor type strain gauges. No. Here we have wide strain gauges. In this wide strain gauges, we have completed the concept of wide strain gauges are divided into bounded and unbounded. We have completed unbounded and bounded strain gauges. Okay. Right. So this is the strain gauges arrangement. This is the strain gauges arrangement in a bridge circuit. Here we have placed 2 strain gauges. One is the active strain gauge, second one is the dummy strain gauge. Here in the bridge we have R1 and R2, two resistance are available. Active gauge and dummy gauge. Dummy gauge we are taking for the reference purpose. Active gauge is nothing but as the original strain gauge here we have taken. So in the bridge arrangement, how the strain gauge we are using is in this way. Right. Semiconductor strain gauges have higher sensitivities. The strain gauge is normally used in a bridge arrangement in which the gauge forms one arm of the bridge. The bridge may be AC or DC actuated. The supply of this bridges may be either AC signal or DC signals, AC supply or DC supply. Only one of the gauges is an active element producing an output proportional to the strain. The other strain gauge, that is dummy strain gauge, is not strained. So in the active strain gauge only we are applying force. In the dummy strain gauge we are not applying any force, just it will be available. But generally this type of dummy bridges we are taking for balancing the bridge. Okay, if the two resistors R1 and R2 have negligible temperature coefficient, the bridge retains its balance under conditions no strain at any temperature within the operating range. In some situations, this resistance is also completely dependent on the temperature parameters. Here we are neglecting the temperature effects and we are taking in the normal situations. The resistance of this dummy strain gauges is not affected by the deformation of the material and it therefore acts like as a passive resistance with regard to strain measurement. So here the dummy strain gauge, it seems to be like as a normal simple resistor. It will give a less amount of resistance value. Since only one gauge responds to the strain causes bridge unbalance just in the case of a single gauge. Okay, so if you are taking a single bridge, single strain gauge, we cannot balance in all the situations the bridge. So for that reason we have taken the dummy strain gauge. Right. Here we have different types of strain gauges. In this, the first one is grid type of strain gauge. Just now we have seen the grid type strain gauge. Next, the Rossetti type of strain gauges. This is the Rossetti type strain gauges. Here we have the vertical directions and horizontal direction and 45 degrees angle directions. That is in the inclined direction also. Here we are representing the structures. So this is the Rossetti type gauge, strain gauge representation. And here we have remaining two types, that is torque type and helical type. Torque type and helical type. So this first one and the third one are the torque type strain gauges and the middle one is a helical type strain gauges. These are the different types of strain gauges are available. You have to draw these are the strain gauges. This type of questions they are asking for 4 marks. Just you need to know about the structures. Okay, next category is foil type strain gauges. Foil type strain gauges. This class of strain gauges are extension of the resistive wide strain gauges. So here it is very important. These strain gauges are completely extension to the resistive type wide strain gauges. So the foil type strain gauges are completely extension to the this resistive type strain wide gauges. The strain is sensed with the help of a foil. The metals and alloys are used for this foil and wire are nickel and constantine, isoelastic, nickel and platinum. So these are the material they are using for forming this type of metal foils. Foil gauges have a much higher, greater dissipation capacity than wide wound gauges on account of their larger surface area for the same volume. For this reason, they can be used as a higher operating temperature range. Also, the large surface area foil gauges leads to better bonding. So here, the foil strain gauges are mostly we are using in the field in the present days because of most of these foil type strain gauges are based on different types of metals which are available: platinum, nickel, constant and isoelastic, nickel. So these are the metals we are using. These are almost all the applications of electronics and biomedical field. These all are the very comfortable materials for all the cases types of energy conversion, energy controlling operations. They have good dissipation capacity, and they have they can manufacture in the larger volumes based on the requirement of the user, and their operating temperature range is also very flexible. So for that reason, these foil type strain gauges are very famous in the field. Now, foil type strain gauges have similar characteristic to wide strain gauges. Their gauge factors are typically the same. So particularly whatever the wide strain gauges has the gauge factor, the same gas factor parameters also available in this foil type strain gauges. The advantages of foil type strain gauges is that they can fabricate it on a large scale and any shape. Just now we discussed we can fabricate a large number of structures and with a required shape. These characteristics together with a greater degree of flexibility allows that etched foil to be mounted in more remote and restricted places and a wide range of covered surfaces. So almost we can fabricate this type of materials with almost covered surfaces with different types of coils also. The transversal strain gauge sensitivity of this gauge is smaller, 1/3 to one side, half of the similar wire gauges. The hysteresis of the foil gauges is also 1/3 to half of the wire strain gauges. With their hysteresis losses also very less with compared to other strain gauges. The term hysteresis is used in the strain gauges, where hysteresis is if the resistance of the strain gauge is measured with no strain applied and the gauge is then stressed to its maximum usable resistance value. The measured resistance after the stress is removed differs the original value. So whenever the stress is observed, it will exhibit one type of resistance value, and the stress after releasing the stress, it will remove the if you remove the stress on that material, automatically the resistance variation going to be back with a small losses. That is called hysteresis loss effect. This inability of the gauge element to resume the exact physical form it had before being elongated produce the difference in the resistance. So whenever you are stretching, automatically it will produce some resistance variations. That is the difference in the resistance is called the hysteresis effect. This type of effect is called hysteresis. So the hysteresis is effect more important in the metal type of foil strain gauges. Okay, the resistance film formed typically is 0.mm thickness. So in the foil, in this foil, the film thickness nearly we are with a density of 0.2 mm thickness we have taken. The resistance values are commercially available for this type of strain gauges are 50 ohms to 1000 ohms. 50 ohms to 1000 ohms. The resistive films. The resistance films are vacuum coated with a ceramic film and deposited on a plastic backing for insulation. Almost on both sides of the foil films, we are making some insulation material to avoid the environmental or temperature effects on this foil. Because of these are very less resistive and with very less density or less thickness equipment. These are affected by the temperature variations which are available in the different areas. So for that reason they are completely coated with some insulating material. So this is about foil type strain gauges. Next, semiconductor type strain gauges. So the semiconductor strain gauges generally we are forming on a wafers. Okay, semiconductor strain gauges are used when a very high gauge factor is required. Generally, with a less gauge factor, the foil type and wire strain gauges we are using. But the semiconductor main purpose of the semiconductor strain gauges are high gauge factor. To have a high sensitivity, a high value of gauge factor is desirable. If you want good high sensitivity, then automatically good gauge factor is required. A high gauge factor means relatively higher change in resistance, which can be easily measured with a good degree of accuracy. Semiconductor strain gauge depends on further action upon the piezoresistive effect. Based on the piezoresistive effect, this semiconductor strain gauge is also working. There is change in the value of the resistance due to change in the resistivity. Unlike metallic gauges, where changes in the resistance is mainly due to the change in the dimensions when the strain is applied to this semiconductor strain gauges, this also works like as the properties of wire strain gauges. They exhibit also like wire strain gauges, but it will give a good sensitivity, a very high sensitivity and a high gauge factor. Okay, semiconductor materials such as germanium and silicon are used further as a resistive material. The semiconductor materials we know, silicon and germanium. These two materials we are using as a wired resistive type wires or foils. Gold leads are generally used for making contacts. Here on the semiconductor material, the conductivity wires are very important. They should transfer the different types of resistance values which are formed on the semiconductor material without loss, with very fast information, with very fast transfer of that voltages, transformation of that voltage. For that reason, they are using gold contacts. Gold contacts are the very good conductors in the conductive type materials. These strain gauges can be fabricated along with an IC op-amp, which can act as a pressure sensitive transducer. So when this type of semiconductor strain gauges are forming, they are manufactured these strain gauges with an op-amp connectivity in that particular IC, like pressure sensitive transducers. The large gauge factor is accomplished by a thermal rate of change of resistance approximately 50 times higher than the resistive gauges. With compared to the wide strain gauges, it is nearly 50 times higher strain. Hence, a semiconductor strain gauge. Hence, the semiconductor strain gauge is as stable as the metabolic type, but much higher output. They have very good higher outputs. Semiconductor strain gauges have high gauge factor about plus 130. So nearly they have 130 gauge factor value, that is the K value. This allows measurement very small strains of the order of 0.0 microstrain. Hysteresis characteristics of the semiconductors is also very less. Strain gauges are excellent. Less than they have 0.05% of hysteresis loss. Life in excess of 10 by 106 operations and a frequency response of 1 kHz, nearly 1012 Hz or 1 kHz frequency range it is operating. Semiconductor strain gauges can be very small in size. We know that the integrated circuits are very less in size, ranging length from 0.7 to 7 mm. So they are very small area occupied resistances or transducers. Next, coming to that, up to now we have discussed the advantages of the semiconductors. Now coming to the disadvantages of semiconductor strain gauges. They are very sensitive to changes in the temperature. So for the temperature changes also they are dependent. So for that reason, this is a major drawback in the semiconductor strain gauges. Linearity of the semiconductor strain gauges are very poor. They are more expensive with compared to the remaining strain gauges. They are very costly. If you manufacture in the large amount, then it is very less in the cost. For the large amount of volumes only, these strain gauges are very useful. With this we have completed the strain gauges concept. Okay, thank you.